Hello there. My name is Dr. John Stressy, and I am here today to teach you some Calculus 2. So I'm creating this playlist of Calculus 2 videos for my students that I'm teaching this semester. You may remember me from such classic as the Calculus 1 playlist that I made last semester. That is the entire extent of my IMDb page, by the way. Like, I'm not very prolific, but I made Calculus videos last semester, and I'm making some this semester for my students as well. So like I said, my name is Dr. John Stressy. My email address, should you have any questions, or if you want to point out some of the errors that you see in these videos, hopefully there's not too many. I'd appreciate it, though. You can email me at jstressy@ufl.edu. So these videos are primarily to help my students, but they're free for anyone. So I hope it does help you, whoever you are, in your study of calculus. So the thing we left off with in Calculus 1 is we left off on integration. And specifically for my class, we left off on the technique of U-substitution. That's kind of the last thing we did. So these videos are going to start from there. And we're going to begin the whole first unit of our class learning more advanced integration techniques. So for differentiation, we had a list of rules. You do want to review those, by the way. If you're not confident on your differentiation, you might want to go to my Calculus 1 videos. Shameless self-plug right there. But we're going to learn more advanced integration techniques because unlike differentiation, integration is not so systematic. There's not really a rule that you would know to do right away. But with differentiation, if you see two functions multiplied together, we've built up this arsenal of rules where you do the product rule and then each individual function has its own rule. So it's very systematic. But integration is very different. So we're going to build up all these different techniques to integrate a wide variety of functions. But first, I would like to start with some basic integration review. So let's just see how much you remember. Specifically to my students, let's see how much you remember here, or if the winter break has made you forget most of the stuff. So, example. That is an integral, the integral symbol right there. So hopefully you remember that. This is the integral of x cubed minus 2x squared minus 5x plus 7 dx. So what this is asking you to do, if you've forgotten, is we need to find the antiderivative or an antiderivative of this function. We're asking the question, what function has a derivative that is this? So we're working backwards, as I was saying last semester. We call this an indefinite integral because there are no bounds on it. So recall that this is called an indefinite integral. Okay? So going backwards, instead of doing the power rule, I would kind of do the power rule in reverse. I would add 1 to the power, and I would get x to the 4th over 4. I hope it's coming back to you now. Then I would increase the power by 1 here, and I would get x cubed. Whatever that new power is, that gets thrown into the denominator. And that 2 was just sitting there the whole time. So this is minus 2/3 x cubed. Moving along, this is x squared. That 2 is going to go in the denominator, and I'll just leave that 5 there. And then plus 7x for this. And then because we have an indefinite integral, you put this plus c. And this is called the constant of integration. So this just lets you know that you could have had any constant here. And if we take the derivative of this with any constant here, we would get back to the original right here that we started with. So this is our general antiderivative of this. OK, I hope that was OK. I'm going to move on to some other ones now. So here's another one. This one is the integral of x times e to the x squared dx. OK, so we did leave off on this technique. This was the last technique that my class went over, and it's called U-substitution. So let me write that. It's U-substitution. The idea is you need to cleverly choose something in here to be u, such that when you take the derivative of u, it magically appears here somewhere, or at least makes the integrand nicer to deal with. So right now we don't have a rule. We will very soon, but we do not have a rule for doing the product rule backwards. We don't have that yet. Soon, though. So we need to use this technique. I'm going to say u is x squared. And the reason I've chosen that is because if you take the derivative of x squared, you get 2x dx here, and x is what I need to get out of this here, so then I can have something easier to integrate. So the integrand's a little too complicated, but once I make this substitution, it'll be much nicer. And even going beyond this, I'm just going to say that du over 2 is x dx. I'm going to divide both sides by 2. So now, if we remove the x's here and transform this into an integral that only has u's, I'm going to get e to the u, because that's what I called x squared right here. I called it u. And then instead of x dx, which is what I have right here, instead of x dx, I'm going to call that du over 2. So this x dx got replaced by du over 2. Remember, a constant in here can just be factored out. So I'm going to have 1/2 and then integral of e to the u du. So here's another review problem. The integral of e to the u here, du, is just e to the u. So I get 1/2 e to the u. This is another integral that was indefinite. There are no bounds here. So I put a plus c. But we're not done. We never had u to begin with. We had x. So I'm going to substitute back in here. So this u, I called it x squared. So this will be x squared right here. And then that's my general antiderivative. And again, the idea is you could take the derivative of this, and you would get back to where you started again to check your answer. So here, what rule would you use? You would use the chain rule. So you can think of U-substitution. U-substitution is chain rule backwards. It's like taking the chain rule, the differentiation rule, chain rule, and taking it in reverse. So this is kind of the chain rule backwards. All right, we're going to review just a little more here. So my last example is going to be the integral of sine of 2x plus secant squared of x dx. So for the third time, I have an indefinite integral. And now I'm just testing to see if you remember your trig derivatives. There were 6 of them. If any of these are fuzzy, go watch my videos, my Calc 1 videos, or just review your notes from last semester if you were my student. So we need the function. Let's just do this separately. It's like two separate problems here because we have this addition symbol. What function's derivative is sine? So that is minus cosine. I'm going to leave the 2x here. And then I need to think if I were differentiating, if I were going forward, I would get this 2 out front because of the chain rule. So I need to actually divide by 2 if I'm going backwards. So the antiderivative of sine 2x is negative 1 over 2 cosine of 2x. Plus, and I just do another one of these problems. So I need to think, what function's derivative is secant squared? And if you are all squared away on those 6 trig rules from last semester, you know that this one is tangent. The derivative of tangent is secant squared. So the entire antiderivative here, the general antiderivative, is this. And I'll repeat it again because it's worth repeating. You could take, especially this part, you could take the derivative of this part using the chain rule, and you can get back to this. And you'll know that that was the correct antiderivative, OK? So these are just a few basic derivative or antiderivative problems just to get us started. But now, what I'm going to show you in the next part of this video is something new. I'm actually moving into Calculus 2 now. I'm going to show you a method called integration by parts. So I'll see you in just a second. All right, welcome back. So now let's take a look at an integral like this. So how about something like x times e to the 2x? So if you try to use substitution here, you might not be as successful as you were before. Take a look at the difference between this integral and the one just before in this video, and you'll see what I mean. So the idea is we have 2 very different looking functions being multiplied together. So we'll need to develop some kind of technique that takes the product rule backwards. So let me write that down. We're looking to do the product rule, but backwards. And the two things you're going to see inside the integrand here are two very different looking types of functions. We say that they're from two different families of functions. X right here, that's a polynomial. So powers of x to the whole number powers. Those are polynomial expressions. And then e to the 2x, we call this an exponential function. So what you're going to see is it's going to be an integral. There's going to be two very different looking things from two different families, basically. Two things that just look very different. And then the technique we're going to be using is called, so we will use something called integration by parts. So that's what we're doing. I'll abbreviate it IBP if I can ever remember to do that. So I might say IBP. And this right here is the statement and the formula that you should remember for integration by parts. So let me go through it with you. So it says, suppose we have two functions, f and g, and they're, again, like I said, they're two very different looking functions. So here we have x and e to the 2x, for example. We have two different functions, and you'd like to calculate the integral of their product. So I'm taking product rule backwards now. So if you call the first function u, and you call the second function dx dv, then the formula to take the product rule backwards, or to do integration by parts, is the following. So the integral of u dv equals u times v minus the integral of v du. So this is our method for taking the product rule backwards, and it's called integration by parts. So I'm going to write here for you, memorize, please, memorize this formula. I will show you a much more efficient way of doing this process in the next lecture video, actually. But you're still going to need to know this for the exam. You're still going to need to know that this is how you set up the integration by parts thing. So I want you to memorize that. Now let's take the rest of this lecture to just do these two examples so I can show you how this works. So my first example is the question I just posed over there. How do I do this? Well, what I'm going to do is I'm going to say, OK, I'm going to let u equal x. So I need to call one of these u. And this, the one I choose for u, I'm going to differentiate. So I'm going to say that du then, what would that be? If I took the derivative of x, I'd get 1 dx. OK, and because I've chosen the first one to be u, that reserves the second one to be dv. Remember, you're not picking u and v. You're choosing something to be u, and you're choosing something to be dv. Don't pick a u and a v. You pick u, and the other one is automatically dv. So the rest of this, after I called this one u, the rest of this has to be dv. So that's going to be e to the 2x dx. And whatever you choose for dv, you're going to integrate this one. So I've kind of made like a little square here. That's how I always do these. So if you integrate e to the x, you get e to the x. But this time, there's a 2 there. So if you think, if you have to go backwards, oh, I'm off the screen a little bit. So let me just scoot that down. Sorry about that. So then v is e to the 2x. But if I go backwards, I'm going to need to put a 1/2 in front of this. Because if I were to differentiate this, that 2 would come in front, and I'd cancel, and I'd get back to here. So I need a 1/2 in front of here. So now that I've got this whole square taken care of, I'm going to go over here. Let me write my formula from here. So all I do now is I say this integral is equal to uv minus, and then v du. And then let me just plug in what I've got. So u is x. V is 1/2 e to the 2x minus. Integral of v is going to be 1/2 e to the 2x. That 1/2, I could just bring it outside the integral, so I just did that right away. And it's v du goes in the integral, so du is dx. So now I've got this. This fairly complicated integral, and now I've reduced it down to just finding the integral of this. And I can do that because I just did that before. I was able to do that in the first step. So let's do this one more time. I'm going to just simplify this. I get x over 2 e to the 2x minus. That 1/2 is just sitting here. Again, the integral of 2 to the x dx, I just did it here, is right here. It's 1/2 e to the 2x. I've integrated it's an indefinite integral, that's what I'm trying to say. So I put a plus c here. And I guess to clean this up, I could just multiply this out. So it's going to be x over 2 e to the 2x minus 1/2 times 1/2 is 1/4 e to the 2x plus c. So this is the general antiderivative of this right here. As always, you can take the derivative. If you're very good at your derivative rules, you can take the derivative of this and make sure you get back to where we started here. OK, let's take a look at this final example. So here I have ln, and then I have x squared on the bottom. So you could think of this as 1 to e ln of x times 1 over x squared. If I really wanted to see the two separate functions that I'm integrating here, like the product rule backwards, if I want to see that f times g here, I could separate it to look like this. Now, often it's hard to figure out, well, what am I going to choose for u? How did I know, in this example, how did I know that u should be x? Well, let me give you just some help here. So the general order of selecting u is, so I'm going to give you kind of the general order of, order of importance basically on which one of them you should make u out of your two choices. So the very first thing, if you see it in the integral, you should make this one u for sure. It's going to be inverse trig functions or logarithmic functions. Logarithmic functions. So that would be number 1. If you don't see any inverse trig or logs, for the next one, you should go with polynomials. More generally, I would say algebraic expressions. What I mean by that is just you see things with powers of x. Because I say polynomial here, but technically 1 over x squared, that's a negative power. It is a very technical thing, but it's not really a polynomial, but it's an algebraic expression. So if you don't see either one of these two things, then the next choice you should use is trigonometric functions. So if you see anything like sine, cosine, tangent, that's what you would make u. And then finally, if you didn't see any of these, then I guess the first choice for u would be exponential functions. Now you're probably going to encounter a bunch of different mnemonic devices along the way to help you memorize this order. Here's one of them that I know that I can give you now, but you're going to hear other ones, and whichever one you like is probably going to be the one you choose. But liate is like a mnemonic device to remember these. L stands for the logarithmic functions and the inverse trig functions. So Li goes with this. A stands for the algebraic function. So A is like the x squared, x to the -2 like I've got here, polynomial things. T stands for the trig functions. And then E is the very last thing in liate, and E stands for exponential functions, like I had here. So e to the 2x. You'll probably hear a bunch of different ones, but this is the one I'm going to use, OK? So now that I've gone through that, what should I choose for u? Well, here I have a logarithmic thing, and here I have an algebraic thing. So if you look at my ranking, logarithmic is always the first choice. So I'm going to go with logarithmic here. So I'm going to say u is going to be ln of x. This will automatically make du 1 over x dx. Remember, the derivative of log is 1 over x. Then that means the leftover stuff is going to be dv. So 1 over x squared dx, it's what's left here. If I integrate this, I'm going to get negative 1 over x. So that's the integral of 1 over x squared. All right, and let's plug it into the formula now. So I'm supposed to do uv minus v du, the integral of v du. My u is going to be ln of x. V is negative 1 over x, so I'll write it like that, minus. Then we're going to integrate v. So v is going to be minus 1 over x. Du is going to be 1 over x dx. So this is my du. So I plugged everything in where it's supposed to go. And remember, this was not an indefinite integral. Finally, I have something called, this is called a definite integral. And all that means is I'm going to plug in these bounds and I'm done. So I have the integral from 1 to e right here. And same here, I'm going to plug in 1 to e as well right here. So this is going to be negative ln of x over x. I'm going to plug in e and 1 when I'm ready. And then here I have a negative times a negative is a positive, so this is plus. What is the integral of 1 over x squared? Well, I just did that. That's right here. It's going to be negative 1 over x. And then I'm going to evaluate this from e to 1. So I took the integral of a positive 1 over x squared because the two negatives canceled. OK, if you plug this in very carefully, here I'm going to plug in e. ln of e is 1. So I'm going to get negative 1 over e. ln of 1 is going to be 0. And then that takes care of this. And then I'm going to do plus here. And then I'm going to plug in e, and I'm going to get minus 1 over e. And then I'm going to plug in a 1 here. So it'll be minus. If you plug in a 1 here, you get minus 1. And then if I can write the answer to that, maybe I can fit this right here. I'm going to get negative 1 over e plus a negative 1 over e is negative 2 over e. And then here I get a minus 1 is going to be plus 1. I don't like how that looks, so I'm going to rearrange it. So the final answer, I'll go over here. It's 1 minus 2 over e. And that's my final answer for that. OK, so keep this order in mind when you're doing problems. This is how you're going to select u. And once you've selected u, dv is all the other stuff. So if you just focus on making the right choice for u of the two functions, you should be good. OK, in the next video, I'm going to show you a much more efficient process of doing integration by parts. It's called the tabular method. So I will see you soon. Thanks for watching.